Okay, so in the last class, we had seen some special casting processes, right? And a summary of that. We had seen die casting and centrifugal casting. And this slide was the last, I believe, that we saw. That lists all the advantages, disadvantages, and the applications, right? Where we are utilizing these processes to make those components that you're seeing on the right, very right. So that is what we saw in the last class. The special casting processes, right? These others are not there as per our syllabus, right? And usually they are not so general. The ones highlighted are the general ones, and that's what is there in our syllabus. So, any doubts from the last class? If there are any doubts, you can ask.
అన్న లిఖిత అంట స్టార్ట్ చేస్తారు హాయ్ బాబ్జీ అని పెట్టింది.
All right. So let us start then. You see gating system in mode, right? We have already seen some part of it. What are the different components in the gating system? But specifically, you're going to see what are their roles, right? I told you, but we have not seen it in detail as to what are the purposes of all these components that we have in the gating system, right? So a typical what do you call casting setup would look like this, right? The sand is not there, but the sand encloses all of this. So start from the pouring basin. As we know, molten metal is poured in to the screw. It goes to the screw base, and then the runner, right? This straight channel is your runner, and then there are multiple gates. Usually there is one gate for a small casting, but multiple for big castings. So this is your mold cavity, right? Basically, once the molten metal flows in, this becomes a casting. So that's a casting, and this is the riser, right? So this is a runner extension, right? After the last gate. So we're going to see what their roles are and what factors should we consider if you want to have a good casting, a sound casting. You want to have what are the factors that will affect a good casting. Okay, so that is what we'll see. You see, as a pouring basin, right? Conical hollow element or tapered hollow vertical portion of the gating system helps to feed the molten metal, right? Initially through the path of gating system to the mold cavity. So the first step, right? It is so designed that you don't have turbulence when you're pouring molten metal. There should not be much turbulence, right? It should flow smoothly to the sprue. So it is responsible for pouring the molten metal, making sure that the molten metal flows smoothly from that ladle, right? You have a ladle, right, which has this molten metal, right? And with the help of this ladle, you are going to pour the molten metal. So this pouring basin is so designed that this molten metal flows smoothly without causing much turbulence, because turbulence causes air to flow inside, right? And we don't want that. We only want the metal to flow inside, not along with air. Okay, so that is what the pouring basin is responsible for. It is responsible for feeding, and not just feeding it without causing much turbulence. Sprue vertical passage made generally in the cope using tapered screw pin. It is connected at bottom of pouring basin, right? Once you have the pouring basin, the next element is screw. It's a vertical passage, right? Generally in the cope, that's the top part of the setup, right? You have two flasks, the top flask and the bottom flask. The top flask is your cope. So it is a tapered screw. I have explained, I believe, why it is tapered. As you are seeing here, it is tapered. A bigger cross section initially and then a smaller one at the end. So it flows from this end to that end. So there's this decrease of cross section. Why is there a decrease of cross section? Someone can recall. Okay, you see, once the molten metal starts flowing in from this end, right? Because you have the molten metal flowing from top to bottom, right? The velocity would increase, isn't it? So if the velocity increases and you have the same flow of molten metal, then as per, I believe you have studied fluid mechanics, as per the discharge, constant discharge, that if you want to have the same discharge, Q is equals to constant. And what is discharge? Discharge is the velocity with is the product of velocity with which the fluid is flowing times the area of cross section, right? If a molten metal, there is a flow of molten metal, right? You would have a cross section, right? If you look at it from the side, what is the cross section of the flow? It could be triangular, right? Based on the uh, container that it is flowing through, right? So that area of cross section. So you see, Q is the product of velocity and area of cross section. So you have this higher area here. If you maintain the same area, the velocity is increasing, as we know, from top to bottom. The velocity is increasing as we go from top to bottom. If this is increasing, right, this velocity is increasing, the product would be increasing. The discharge would be increasing because the velocity is increasing. But if you decrease the area of cross section proportionally, right, proportional decrement of area of cross section with increase of velocity will ensure that discharge is constant. We want to maintain constant discharge. That's the principle, right? There should be constant flow of molten metal, right? The same amount of fluid that is here, we want the same amount of fluid to be here, right? So how do you maintain the constant discharge? Discharge is a product of velocity and area of cross section. If the velocity is increasing, we must make sure that the area of cross section is decreased so that we have constant discharge and therefore no air should come inside. If you have the same cross section, right? This is your top part, this is your bottom part, both have the same area of cross section, but because the velocity has increased, right, then the flow of model will be like this. Let me draw it with another color. It will be like this. Because the velocity has increased here, the area of cross section, the area that is required is less. You can observe this when you open the tap. If you open a tap, right, here at your home, you can observe that when that fluid is flowing, there will be a lot, what do you call, a thicker uh, amount here, right? A thicker cross section. But as it moves along, it increases. I'm sorry, it decreases to a point, almost like a point, because it is gain velocity, right? To maintain the same discharge, this will reduce in cross section. I hope I'm clear with the example. So this is what is the concept behind that tapered screw. Is that clear? Okay. So that is what is the roll of a screw. It is tapered with its bigger end to receive the molten metal. The smaller end is connected to the runner. It helps to feed molten metal without turbulence to the runner, which in turn reaches the mold cavity through gate. Right? Should be able to feed without turbulence. And how do you do that? You maintain a tapered section so that the discharge is constant and therefore there would be no turbulence, no air would come inside along with the molten metal. So that in turn, right, so that the molten metal reaches the mold cavity through gate, right? That's the other part of the story. So now you see it should have been runner first. We will go in order, okay? So you see here you have a screw base. So once it passes the screw, there's a screw base. Basically, it is to take down any impurities, right? You can see this is at the bottom, slightly down to this runner, so that the impurities would settle down here. Any sand that is eroded, if at all, would settle down here. Impurities would settle down, and therefore only the molten metal is allowed to go inside the runner. Okay, that's the screw base. I hope that is there. Okay, so that's about screw base. Now you see it comes to the runner. Now what happens? This is a channel which connects the screw to the gate, right? While stabilizing the flow of molten metal, that is avoiding turbulence and gas entrapment. The role is to stabilize. You can see what I've highlighted. The role is to stabilize the flow of molten metal, right? It has entered the screw. As I told you, the velocity is increased. That is for sure, right? The velocity is increased. Now the responsibility of the runner, you see here this part, all of this, is to make sure that that increase of velocity is stabilized, right? There is stable flow. So that happens in the runner. Tries to stabilize it. Whatever high velocity fluid has come, it tries to stabilize, bring it down to normal speed, and hence the molten metal can enter through the gate, right, to the mold cavity. That's what the role of runner is to stabilize, right, to stabilize the flow of molten metal. Now you have gate, right? After the runner, it goes to the gate. Now it is a small passage or channel being cut by gate cutter, which connects runner with the mold cavity, and through which molten metal flows in to the mold cavity, right? Flows to fill the mold cavity. It feeds the liquid metal to the casting at the rate consistent with the rate of solidification. So yes, this is important. It should be able to feed the liquid metal at the rate consistent with the rate of solidification, because if the rate of solidification is not maintained, then the molten metal would solidify here itself, right? It partially fills the cavity and then it solidifies. So the gates should be properly kept, right? The number of gates and the cross section of the gate should be so designed that your molten metal should flow into the mold cavity before the solidification starts, right? It should be able to reach all corners of your mold cavity, and then the solidification should start. So that has to be ensured by providing proper number of gates and the cross section of the gate, right? And choke, it is that part of the gating system which possesses smallest cross section area. In choke system, gate serves as a choke, But in free gating system, screw serves as a choke. Okay, it depends. If it is a choke system, then your gate serves as a choke, isn't it? As you can see, here you had a higher cross-section area, greater cross-section area. But as soon as those gates, it enters the gates, you have a smaller cross-section area. So it basically acts as a choke, right? Just as your bottleneck, right? Any normal bottle, the top part of it you call bottleneck, right? Basically where the flow gets hindered. So this is what serves as a choke here in this example. So K depends if it's a choke system. In free systems, screw serves as a choke. Other thing is riser, right? Which is at the end, right? Once it fills the casting, then you have the role of the riser. Because once it fills the casting, it will flow into the riser, right? So that we can know one purpose of the riser is, as we have discussed earlier, it helps us to know whether the inside of that mold cavity is filled or not, right? Only when it is filled, then the molten metal would come to the riser and this will come to the top, right? The riser would be completely filled. So that is one purpose. Other thing is, right, it is a passage in molding sand made in the core part, right? Core portion of the molten metal rises in it after filling the mold cavity completely, right? Other thing is, this is also we have discussed, it compensates the shrinkage during solidification, right? That's the role of riser, that upon solidifying, right, basically in liquid contraction also, right, before it turns into solid, even when the liquid is when there is a decrease of temperature in the liquid state, there is still contraction, right? That is liquid contraction. We've discussed three types of contraction: liquid contraction, solid contraction, right? So basically liquid solid, and solid, three contractions, right? What we have discussed earlier. Liquid contraction when it is contracting while in the liquid state. Liquid solid contraction while it is contracting when it is converting from liquid to solid, right? While it is converting. And the third one is solid contraction when it is completely what do you call solidified, then also it contracts. Complete solid contraction we can call. So this riser is responsible for shrinkage during the solidification of the casting, thus avoiding a shrinkage defect in the casting. So this compensation of the shrinkage, right, is when it is solidifying from liquid to solid, right? That's what this does. It is not responsible for solid contraction, right? It will not compensate because it is solidified already. So that would no longer be a useful purpose of the riser. So that is the reason, and also permits the escape of air and mold gases. It promotes directional solidification also, right? Keeping the proper riser at proper positions also helps to ensure directional solidification and for the escape of air and mold gases, right? They can come outside through that riser system. Chaplets, right? These are metal pieces you can see here, inserted in a mold either to prevent shifting of mold or to locate core surfaces. Two reasons. So either that the mold cavity does not shift, right, as a support, right, or to locate core surfaces. Where should those core surfaces should sit, and basically to support the core surfaces also, right? The resistance pieces in form of chaplets are made of parent metal of the casting, right? If aluminum is what you're casting, then the chablet should be made of aluminum. Its main objective is to impart good alignment of mold and core surfaces and to achieve directional solidification, right? Alignment of the mold and even the core surfaces and to achieve directional solidification also, because once you have kept those chaplets, they will also act as a heat taking source. I'm sorry, heat taking component, isn't it? Because to be able to melt those chaplets, it requires energy. And where do you get the energy? From the molten metal. And if the molten metal gives it the energy, the temperature goes down. So all the molten metal which is surrounding the chaplets will experience a decrease of temperature faster than the molten metal which is away from the chaplets. Right? I hope I'm clear with the point. This molten metal would not solidify early. This would solidify early because of the fact that it has to give energy or precisely thermal energy to these chaplets, right? For them to melt, right? Its main objective is to impart good alignment and to achieve directional solidification. How directional solidification I have explained, right? So that you can have a solidification of some part of the casting earlier than the other parts. That's directional solidification. Okay, I've explained this time and again. So here you can see different types of chaplets, right? Riveted chaplet, welded chaplet, double-headed chaplet, right? So you see, they are there to support this core also, right? And ensure that this mold, right, the other sand does not come into contact with the core. So that is what the chaplets are for. Doubts so far? Okay. You see here another example of using this chaplet. How do you hold this core, right? This is basically acting as a cantilever, right? So you have to have some support, otherwise this would come down because of this weight, right? Gravitational force, right? Out of its own weight. So to be able to support this core, right? These chapters are provided here in specific example. Chills, right? This is where we are discussing chills. We haven't discussed them till now. In some casting, it is required to produce a hard surface at a particular place in the casting, right? It is required. That's one requirement that we have to be able to have a hard surface at some part of the casting and not so hard at some other parts. So how do you achieve that? At that particular position, the special mold surface for fast extraction of heat is to be made. The fast heat extracting metallic materials are known as chills. Will be incorporated separately along with sand mold surface during molding. After pouring of molten metal during solidification, the molten metal solidifies quickly on the metallic mold surface in comparison to other mold sand surfaces. This imparts hardness to that particular surface because of this special hardening treatment, right? To fast extracting heat from that particular portion, right? So those are your chills, wherein you're trying to extract heat from some part of the casting, right? Some part of the mold cavity, so that it the hardness property can be manipulated. You see all the types of chills that we have. You see, this is one chill. This is your core part, and this is where the molten metal will flow in, right? On that white, what you're seeing, this one, all these, this will be filled with molten metal, right? So to be able to harden this part of the casting, you're providing chills. Here also, same thing. To be able to harden this part of the casting, only here, right? So this casting here, this part would be harder than the other parts, right? Maybe here as compared to here and here. This would be more harder because of the extraction of heat by the chill, right? You have internal chills also, right? If those internal features which are uh, not at the surface of the mold but inside, then you have to provide these kind of chills also. Direct and indirect also, right? Direct in contact has more influence. Indirect, a lesser influence, right, as compared to this direct one. But still, this kind of acts as a heat extraction uh, component. Okay, so all these are kinds of chills you can see, right, depending upon requirement and the geometry of the casting that we are trying to cast. Now you see the principles of gating design. What principles should we keep in mind, right? These have come out of experience. The following factors must be considered while designing gating system. Sharp corners and abrupt changes in any cross section or portion in gating system should be avoided for suppressing turbulence and gas impact, right? Sharp corners in the sense like this. These should be avoided. It should be so ensured that you have proper fillets so that it will flow smoothly and there will be no air coming inside, no gas entrapment, and no turbulence, right? That's the first step. There should be no turbulence and therefore follow through. So no gas, etc. So abrupt changes should not be there. Like for example, you have this, and then suddenly the cross section you have increased. So from here to here, there will not be smooth flow of model metal, right? Or from here to there, vice versa. So have to ensure that no sudden cross section changes are there. That's what the first one says. So the relationship must exist between different cross section areas of gating system. The most important characteristic of gating system besides sprue are the shape, location, and dimensions of runners and type of flow. It is also important to determine the position at which the molten metal enters the mold cavity, right? So other than sprue, you have runners, right? Shape of runner, location of the runner, and dimension of the runner are important. And the type of flow that we're trying to look at. So where the molten metal enters the mold cavity is important, right? What points have you kept? If it is a big casting, this becomes very important. Gating ratio should reveal that the total cross section of sprue, runner, and gate decreases towards the mold cavity, which provides a choke effect, right? So all through from sprue to the runner to the gate, right? The gating ratio should decrease, right? So you are trying to slow down, right? Just as if you have seen some, what do you call, road sections, right? You have a higher width, I mean a larger width, and then they decrease the width slowly, right? And then if it is required, they will decrease it more. So you have a smooth transition here, right? Instead of having like this, right? So properly channelizing it. So what they are trying to say is the gating ratio should reveal that the total cross section of sprue, runner, and gate decreases towards the mold cavity, right? As we are moving on from the sprue to the runner to the gate, it should be decreasing, right? So this provides a choke effect, right? Bottleneck, basically. So that's what is there. And bending of runner, if any, should be kept away from the mold cavity, right? And basically providing those fillets, right? And the runner should be straight. That's what the purpose is, because that will ensure that all the gates will receive the same amount of molten metal. Developing the various cross sections of gating system to nullify the effect of turbulence or momentum of molten metal, right? The different cross sections in the gating system, right? Like for example, your runner, your screw, your gating, right? The cross section is so decided that it nullifies the effect of turbulence, right? Smooth flow is to be maintained, so turbulence is to be nullified. Or momentum of modal metal, right? The mass and the velocity with which it is flowing through, the product of that should be optimized, right? The momentum. Streamlining or removing sharp corners at any junctions by providing generous radius, tapering the screw, providing radius at screw entrance, right? Even at the screw entrance, you provide that kind of fillets instead of having like this, right? You're trying to have some filleted portion, right? So providing radius at the screw entrance, tapering the screw, we have discussed this, generous radius, right? Fillets basically, right? Technically we call them. So that is to be ensured, right? Now you see the types of gates. What are the types of gates that we have, right? In the sense, this gate, right? I hope the point is clear. What are the different types of gates we have? So we have, just as we have different types of pattern, different type of what else have we discussed? Pattern and what else was it? Sand also, right? Types of sand also we have seen. So the types of gates, right? First one being top gate, bottom gate, branch gate, horn gate, and parting time. You see, top gate, as the name suggests, the molten metal is poured directly, right, from the top. Molten metal from pouring basin, right? That's your pouring basin. Is fed directly into the mold cavity, as you can see, flows directly inside. The hottest metal remains at the top of the casting. This promotes directional purification from the casting towards the gate, right? That's what happens because your molten metal is flowing from the top. The fresh molten metal is there at the top, whereas the old one is down at the bottom. So that's what they're saying, that the hottest metal remains at the top of the casting. This promotes direction solidification, right? Because the bottom part will solidify first, like that, from the casting towards the gate, isn't it? Here to there, the direction of solidification. Bottom gate, as the name suggests, molten metal enters from bottom to the mold cavity. It minimizes turbulence and erosion in the mold cavity. So, unlike your top gate, the molten metal would not be having this turbulence and erosion problem here because we're trying to send it from bottom. So it fills from the bottom to the top, like that. The cavity is filled from the bottom to the top, unlike top gating. Top gating system wherein it starts coming in from the top, right? So it provides unfavorable temperature gradients that do not promote directional solidification, isn't it? Unlike your top gate. Horn gate, right? This type of gate, which is a part of the pattern with smooth curves and progressive change in dimension, is designed to minimize mold erosion and oxidation of molten metal, right? As you can see, horn type, right? So smooth curves are provided, right? Basically to, as we have discussed, to avoid mold erosion and oxidation also, right? So to avoid all those problems, we're keeping these smooth kind of curves, basically horn shape. That's why we're calling it horn